Okay, so yeah, so now we have this formula for Hamiltonian, and so the formula can be written in a simpler form: n multiply c and ni multiply ci plus some we have just ignored, and here c and ci and can be written this way. And here there's a remark about this di. This is a covariant derivative, but now this covariant derivative is acting on a tensor density. So Tij is a tensor density. So this covariant derivative is actually not exactly the covariant derivative we have learned before. So this is actually, although I use the same notation d, but this is it's a little subtle here. So this is covariant derivative. Covariant derivative of tensor density. So it's different from the previously learned covariant derivative. Okay. So when you do the derivation, you will see the result. So which means let me put the homework is that derive both A and B. Derive A and B. So derive both A and B, these two formulas. And in the derivation from A to B, which you involve in the integration by part, moving di from n to p, so you will see the explicit formula for this covariant derivative if you do them rigorously. Okay, so now let's give you a definition. What is exactly this covariant derivative for tensor densities? So now let's consider a arbitrary tensor T of arbitrary tensor density T. So here I don't put a twiddle on because suppose this is weight of m. So before I put a twiddle because this is weight 1. Suppose it's weight 2, I have to put 2 twiddles. Suppose it's weight 3, I have to put 3 twiddles. But suppose it's weight 10, then I have to put 10 twiddles. I don't really want to do that. So therefore, I put a m in the round bracket on top of t. It just indicates that it has m twiddles. Yeah. It has some indices a1 to an and b1 to bn. Okay. So this b to bl. And so it is called a tensor density of type NL and weight m. Tensor density of weight m. Okay, and what it is? Usually it is written. Usually this tensor density of weight m is related to a tensor up to a prefactor, which is determinant q to the power m. P a1 an b1 bl. Right. And this guy, this t is a tensor. It's a tensor of type K NL. And here m is always a integer. Here, m is always integer. So we don't consider tensor density of weight 1/2 for any other fractional power. Okay, so now when we consider covariant derivative, well, I mean, let me put a g. So this is for arbitrary dimension or arbitrary signature of the metric. Yeah, and then the covariant derivative I still denote by nabla mu act on the tensor density. So here I'm talking about the covariant derivative act on tensor density and the component of this derivative. And then mu L. And then the first term, it is just the same as ordinary derivative. It's just a partial derivative. mu L. And so here the components of this tensor density is just the components of this tensor multiply this determinant, square root of determinant to the power M. And then you have to plug, remember that for the ordinary covariant derivative, you have to put a lot of crystal symbols, and a lot of terms relate to crystals, and you still add them here. So you will have, well, so let me put that explicitly. Gamma mu I mu alpha. And so this is the I slot. Mu1, mu L. And you plug in and you plus. Sorry, this is J slot. So this is sum over J. It's mu J. Okay. So this is gamma alpha mu. Yes. Mu J. One alpha mu L. So this is J's slot. Okay, and then you have to. So this would finish if it was a ordinary tensor, right? But now it is a tensor density. So you have to add another term, which is M minus M. M is the weight, and you have to have a trace of gamma, trace of crystallization, alpha alpha mu, trace of the previous two indices, and then multiply T M. So it's not really a, so last term is not really a contraction between gamma and T, but just this trace of gamma multiply T. N, U1, UL. Okay, so that's it. So this is the covariant derivative of tensor density. So this is a general definition of covariant derivative. Derivative of tensor density. Okay, a good thing about it is that, and remember, the reason we need a covariant derivative is that after the covariant derivative act on tensor, and the result is still a tensor, still transformed nicely as a tensor. So here is the same. So once you have a covariant, once you have a tensor density, you use covariant derivative act on it, and the result is still transformed as a tensor density, still transformed in the same way as a tensor density. So that's why you need the last term. Yeah? And that's the reason why you need a last term. Okay, and similarly, because in the end we also need a Lie derivative of tensor density. So here also we need to define, later on we will use it, the Lie derivative of tensor density A1, then B1, BL. Okay, and this is just defined to be, so firstly, the ordinary Lie derivative. Similar to the covariant derivative, you see the covariant derivative is just defined by the ordinary covariant derivative minus additional term. So here the Lie derivative is the same, it's similar. So this is just the Lie derivative, ordinary Lie derivative, as if this guy is a tensor. You see if what's the tensor? And plus additional term, plus M, again relates to the weight, and T M. Okay, then B1 BL, and then multiply covariant derivative dA, dA, and V is the Lie derivative, the vector which you define Lie derivative. Okay, and yeah, and it's defined for all. Remember, Lie derivative definition of Lie derivative is defined for all all covariant, for all torsion-free covariant derivatives. So here is the same. So it is for all torsion-free covariant derivative. And the point of those definitions is that guarantees the result of derivative is still a density. Guarantees that covariant derivative act on tensor density is still a tensor density. For Lie derivative. So basically the transformation rule will be preserved by the tensor density. So I'm specifically the transformation rule here is the same, but I write it down for you to understand. The transformation rule for tensor density is T prime. Let's say it is 1,1 type tensor density. It is given by determinant of Jacobian. If you do a coordinate transformation to power m, I think it's primed. T sigma. Okay, so you see the last part. So this is wait time. You see the last part. It is just a tensor transformation, but the tensor density transformation you just add a prefect. Okay, so this is the transformation rule tells the difference between tensor and tensor density. Let me see. I think I have to stop here. Okay, yeah. So probably it's a good time to stop. All right, we continue next time.